So, today the last seminar in this semester, and I hope you have a New Year's mood. I have. So, and today we will talk about unsupervised learning approaches. Um, the main difference between supervised learning and unsupervised learning that in supervised learning we have some labels and we try to learn train models other they that these models could predict with labels, or some numbers if we talk about regression tasks. So in unsupervised learning, we don't have some labels. We want to split our data into some cluster based only on structures in our data set, some information patterns, what our data examples have, but without some labels. Sometimes we have some labels for validation, and and in this case we can use scores, some scores that need the labels for computing. But yes, in the general case, we have unlabeled data, and we try to cluster this data to different groups based on some informational patterns, and and also we try to understand. We can try to understand the quality of our clustering, for example, based on the topology of our clusters, for example, without some labels too. So on this seminar, we will work with a data set contains texts. Each text is in use, and we will have around 20,000 uses in our corpus. Thank you for joining to this seminar, and I repeated again about task, what we are planning to solve today. We want to apply different clustering techniques for text corpus. We will work with corpus contains news, and we'll try to cluster this news to different groups. So we will work this dataset from sklearn. This dataset contains 20 news groups, but we will select only 11 because we will want to visualize our clusters, and yeah, if we will use all 20 groups, we will have some messy plots. So based on this reason, I just selected 11 groups for more clear visualizing. So, okay, we have 11 different groups and around 6,000 texts. Each text is some news. We can see that each text contains not only information about what happened, but also some technical information like mails and yes, subjects and organization. We today we will work this each text like just a text, but um, if you have some technical information from in your texts, better to select this information in different feature types. Yeah, for example, you can select emails and subjects like a different fill features in your item. And yeah, and for example, you can have different modalities for clustering your data set. And for example, make some experiments, use only text or use only subject, and maybe join in different proportions these modalities. Yeah. Okay, but now we will treat our examples like a plain text. Okay, this code, it is just for relabel our labels because yeah, we selected some 11 classes. Yeah, we will use these classes only for visualizing our clusters. Yeah, but all our training yeah will be without clusters, of course, because today we will try to work with unsupervised approaches. Okay, this code, it is just for renaming labels because we want to have labels from 1 from 0 to 10. Yeah, just some technical code. Okay, now I have a question for you. So we will work with texts and we will cluster these texts into different groups. I think you listened in the lecture that the most approaches in clustering based on measure some distance between two vectors. Yeah. For example, Euclidean distance between two vectors. But now we don't have vectors. We have just text. So, question for you: how could we transform each text to some vector? What approaches do you know for that? Um, I'm looking for your ideas. You can write in chat. How do you think how we can transform text uh, to vectors? Okay, one seminar ago, we worked with these recurrent neural networks, and we worked with texts too, and yeah, we split it each each text to tokens, and worked with each token like as a categorical feature. So, and yeah, we used one hot encoding approach. So, how do you think? And yes, in this approach, when uh, we need to process each token, our text was represented as a matrix. But now we want one vector for all our text, for all our tokens. How do you think how we can create one vector for representing each text? It's okay. It's very, very very simple approach. Just yeah, again, split our text into tokens. In this case, each token is a word. Yeah. One seminar before, each token was a character, but now each token is a word. And yeah, we can just count the number of each token in each text. And yeah, it this approach named count vectorizer. And also there is some some more little bit more complex approach, TF-IDF. The main idea of this approach that we want to decrease the frequency of very frequency words. So we know that that there are a lot of words like and, or, I, me, and something like that. Based on these words, we we can't understand the topic of the current text. So, and yeah, these tokens um, don't have a lot of information um, for classification, for clustering, and yeah, the main idea um, to decrease the influence of this type of tokens. So, and TF-IDF, it is score um, which has two main parts. The first part, it is just counting the frequency of the current term in text, in the current text, but also we need to count the frequency of the current token in documents in our corpus. So, and yes, and this the second part of our score, inverse document frequency, helps us to decrease the influence of non-informative tokens. So, the question for you again, based on the information what I now provided to you about TF-IDF, how do you think the score of 4 words like the and will be low or high? How do you think? Guys, I need to understand that you understand what are happening now. And yeah, how do you think? The TF-IDF score, for example, for word the, will be low or high? Yeah, only two options.
Will be high.
Thank you for your answer, but no. The TF-IDF score for word there will be low because yeah, it is a very frequency word. And for example, if we take some text and start and we'll count the number of words there in the current text, yes, frequency of this word will be high. But and for example, if we will use count vectorizer, yeah, in this case we will process the word this really high score. But the main idea TF-IDF to make the score of this word low lower by 18 by multiply the frequency by inverse document frequency. What it what it means. So we need to count now how often this word there is appearing in documents in our corpus. So, and we can find that this word appears in a lot of texts. So, and yeah, we will use inverse document frequency. So we will use some parameter for decreasing the term frequency in our text. Yeah. So yeah, the main idea of TF-IDF to decrease the score of this word, because this word appear often in the texts of our corpus, and we don't we couldn't to split texts by this feature into different groups. So, and we don't want to make a lot of attention to this kind of words. So yeah, but again, thank you for your answer, and now I understood that I need to give more information about this approach, and please feel free to answer me. Okay. We can use TF-IDF vectorizer from sklearn. Okay, this we need to fit TF-IDF vectorizer based on our corpus. How do you think during this fitting process, what we will collect? What parameters we are training? How do you think? Okay. When we need to transform texts into vectors, we need to split. The first step is splitting our text into tokens. After that, we need to collect the unique tokens and form a vocabulary. Based on this vocabulary, we will form the vectors, yeah, and we will use each word like a categorical feature. Yeah. After that, we need to compute the the frequency of each word in vocabulary in each text. And after that, we need to multiply the sum as a value which compute based on the frequency of each word from our vocabulary in documents in our corpus. So we need to create vocabulary. We need to count how often each term appears in each text, and the third part, we need to count frequency of each term in documents of our corpus. So yeah, we have three parts. What we need to do for create a vector for each text. How do you think? What parts from these three parts we need to train during the fitting process? Hi guys, any ideas? We need to have vocabulary, TF, and IDF, three parts. What of these parts we need to train? So, of course, during our theta process, when we call the fit method of our corpus, we first of all we form the vocabulary, and also we need to count the IDF score. Yeah, we need to count how many times each token appears in documents in our corpus. So yeah, and based on this information, we can we can transform each text. Yeah, during a call the method transform. So yeah, and you need to understand that, for example, if we will create some pipeline for make predictions, and we will use TF-IDF vectorizer, we will train TF-IDF vectorizer on our train part of our data set and make a transform on the train part and the test part. So if we will create pipeline, we will train vectorizers only on train part of our data set. Yeah. You can't to transform all your data set. After that, to train model on the train part and make predictions on the test part. No, please train vectorizers and other transformations only on the train part too. So, yeah, KFID vectorizer have some parameters like max document frequency, mean document frequency, stop words. For example, stop words, it is just a list of words like there, and, or, and these words what don't have a lot of information for clustering or predict some topics. So yeah, and also there are two parameters what help us to decrease the length of our vocabulary. For example, we can say that we don't have analyzed the tokens what that don't appear often in our documents. For example, if the token is in only one document, so I think this feature can't be very important because we couldn't select a group of texts based on this feature. So yeah, and we can increase this low boundary for making for selecting only tokens what appear often in your documents, and yeah, and will help you to split documents to different clusters. Yeah. So we can see how the length of vocabulary is changing when we increase the mean document frequency. So, and for example, we can decide that we will work only these tokens that are at least in 10 documents. So yeah, let's try to use mean document frequency is 10. In this case, we deleted many non-useful tokens. Yeah. So, but if you clean some tokens, if you want to clean some tokens and deleted some tokens from your corpus, you need to check there are empty documents after this cleaning process or not. And of course, if there are some clean some documents that don't contain some tokens after cleaning, yeah, you need to delete these documents too. Yeah, this code just for that. Okay, so we selected some vocabulary, transform our texts to vectors based on this vocabulary, and now we try to visualize these documents. For visualizing, often the TSNE approach is used. So I think you had a lot of information about this approach in the lecture, and this approach is used only for visualization. Could you say me why? Why this technique for the dimensional reduction isn't used for for selecting features, for adding this approach into pipeline, for example, in the production, or maybe clustering system or classification system. So why the TSNE is used only for visualization? Do you remember? Guys, please give me any your ideas. So let's see how TSNE is working. So first of all, we need to create we need to compute the probability distribution for our data in our current space. And after that, we will try to find other representations in low dimensional space, but in the way that the probability distribution from our current space will be close to the probability distribution of in the target low dimensional space. For that, we will use Ulbach labeler divergence, for understanding how close our current distribution. This the distribution what we try to create, and in this case we compute the computer probability probabilities of our current data based on all our items. And and if we will add one more example, our distribution will change too, and we need to compute again the low dimensional representations based on the new distribution. So we need to understand that we, using this approach, we can just take some data set, apply this approach to this data set, and get the new representations only for these examples. We can't to fit this approach and transform the new items based some trained weights or statistics or something like that. And in this case, and we don't have some options to work with new data using this approach. So I think this it is a main thing why this approach is used only for visualization. Okay, try to visualize our data. We need to apply t-SNE to our TF-IDF vectors. And yes, let's see. So these colors added by the classes what we have, and we can see that TSNE try to save the distance between our objects, and try to we can see that some groups of our texts lie really close to each other, and we can hope that our that approaches for clustering can capture this structure and can cluster too. Yeah, it is a good good technique for looking to your data set and maybe understand something about topology of your clusters of your data. So yeah. Another way to reduce the number of dimensions, it is to use PCA. So let's try to use PCA for visualizing too, and try to select two main components too, like in like by Tiffany. So, and in this case, uh, we don't have a beautiful visualization of our data, but we can see that PCA tried to select two two main components. Yeah, you can see this green dimension and this red. Yeah, and you can see that PCA try to use try to select components that are orthogonal each other. But yeah, we can see that this approach, in our case, is bad for visualizing. Yeah, for because PCA doesn't save distances between objects. Yeah, this approach doesn't guarantee this, but uh, but this approach has some other very cool features. For example, this algorithm are working this centered data and transform to other centered data. So yeah, our data will be normalized, and it is great for working for training linear models on the representations after PCA. So also this approach try to select the components the biggest biases because we need to have more information for try to split our data to different classes or different clusters. And yes, this approach can guarantee us that we will select um, the features. These are the biggest biases. So yeah, and it is really helpful for us. If we will, and also we can use with approach for processing the new items. We can fit this transformation on our trained data, and after apply this trained transformation to our test data. So yeah, and what we will train in this case? How do you think? Now here you can see the process, um, how we transform each vector to the new vector in lower dimensional space. And yeah, how do you think? What do we train in this approach? So of course we need to uh, collect um, the mean of each feature. Yeah, we pre-computed these uh, statistics. Also, we need to um, we need to compute eigenvectors and eigenvalues. Yeah, I want to recommend you to read more carefully about how this approach is working, and yeah, and understand what we train during the when we call train method in Scalor. Okay, but in this case, the number of components what we will select is a hyperparameter, and we will need to understand how much components we want to select for for creating the best solution. So yeah, how there are different techniques how we can do that. For example, yeah, we can select it. We can select the number of components based on the variance ratio. Uh, yeah. Here we can see the line of how this score is changing during during adding some more components, and yeah, for example, we can notice that using around more that more than 300 features don't add some more information uh, to our representation of vectors. So yeah, for example, we can decide to use 300 components, and in this case, we uh, we will reduce the half of parameters, and yeah, it is a good results, but yeah, we will reduce the half of parameters, but we will not lose a lot of information, yeah, because yeah, we could see that we will not lose a lot. So yeah, but also we can try, for example, 200 parameters, and we'll make some experiments, and maybe it will be enough for our task too. So okay, but now try to use 300 features. Okay, also there are some other ways. For example, we can set a variance threshold, and yeah, um, we can say that we want select want to select the minimal number of parameters in case we will lose only 5% of our information. Yeah, you can apply this approach in this way. And also, of course, if we are solving supervised task, we can treat this hyperparameter as another hyperparameters, and try to understand the beta value uh, uh, for this hyperparameter based on cross validation approach. Yeah, just check the quality of your model on your data set, on your data set for validation. So okay, now we will try to use two different approach for clustering, comments, and DeepScan. Begin to use begin these comments. So yeah, this approach is a really simple approach. We need to randomly select some number of centroids, and after that, just to compute the distances of for each vector to each centroid, and um, and add um, add um, each object to the group this the most close centroid. So after that, we can update centroids and yeah, repeat again and try to again understand the uh, the nearest centroid for each object, for each vector. Yeah, very simple approach. And yeah, if we are using um, the standard commands, in this case we select centroids randomly. But for example, we can select uh, bad centroids and for example centroids what lie really close to each other, and in this way we mm, we could join um, join two clusters um, really um, close to each other neighbors, but couldn't split mm, some more uh, some examples that lay more. Yeah. So based on how you will select these centroids, your result, yeah, the result is really sensitive to how you will select these centroids. So, and for fixing that, um, add some uh, additional technique for selecting centroids, and this improved approach called K-means plus plus. K-means plus plus, it is just an approach, this other this other technique for selecting centroids. Now we select the first centroid randomly, but each next centroid we will select uh, as far as possible from selected before centroids. So yeah, we don't want to select centroids what are close to each other. And yeah, this thing um, was fixed by K, K-means plus plus. Okay. Mm. Here the number of clusters is a parameter too. We need to establish how many clusters we want to select before uh, before apply this this approach to our data. And yeah, there 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 are different techniques how we can do that. For example, we can make a decision based on two scores. First, this in cluster sum of squares. Uh, so for computing this this metric, we need to we need to align the cluster to each point, and we need to compute the distance from each point to aligned cluster, and after that we need to get the mean value of these distances. And of course, if we will increase the number of clusters, this score will become less and less. It is normal because we may but it is normal but because we add more and more clusters, more and more centroids, and each element will become more and more close to some centroid. So, but in this case, meaningful how fast our score becomes less. So yeah, you need to see to the speed of becoming less. So yeah, maybe the good idea is computing the gradient, maybe, or something like that. Because yeah, you need to understand. You need to understand the speed of your changing. So and other score it is a silhouette score, and try to use this score, and yeah, um, of course sometimes we can see that for example our score become less after after we added one more cluster. For example, the score for 4 cluster was better. The score for 5 clusters. So yeah. Also, for example, here we can uh, notice that the score for 11 clusters is better uh, than the score for 12 clusters. And yeah, we can, but of course, after this local maximum, our score started uh, to increase again. And it is normal, but in this case, you need to pay attention to local maximums. For example, you can decide to select 4 clusters or 11 clusters or 16 clusters. So yeah, but we remember that we have 11 classes, and it is good result that our model for clustering is sensitive um, for 11 clusters too. And yeah, just try to split our data to 11 clusters. So yeah, here we fitted our comments um, for 11 clusters, and yeah, I can show you that sometimes for analyzing your data, your results, you can use some untypical untypical scores for this type of uh, task. For example, I think in lecture a lot of scores were mentioned, but I think you the confusion matrix wasn't mentioned for analyzing the quality of your task, of your result. But why not? The confusion matrix, it is just the tool for understanding what classes we have as target and what we will predict and what we predicted, and that's all. We have a cluster, we have classes, and we can use this information for understanding uh, for example, to capture uh, to split our model for clustering our data in the same way as as classes we have or not. And for example, we can see that uh, our unsupervised approach to split uses from classes to two different clusters. Yeah, and for example, we can pay attention to these two clusters and maybe understand that uh, the class 2 of our news have some subclasses and yeah, and also we can see that our approach um, smooth all elements from zero classes through all clusters. It is a interesting result too, and we can pay attention to this thing too, and understand why it was happened. It happened. So yeah, um, I just want to say you, please be creative. If you know that some approach from other area, from um, other tasks can help you for understanding something about the quality of your data, the quality of your model. You can use it. You can try to use that. Yeah, and if you can make some assumptions based on these different approaches, it is good. So yeah, try to see how Cummins clustered our data, and yeah, we can see that we have um, isolated good isolated clusters, and it is really similar these classes what we had before, and yeah. Okay, there one more approach, DBScan. I can say that DBScan um, have a really good feature. We don't need to select the number of clusters. Uh, DBScan can do that automatically, but of course we need to select other parameters. We need to select epsilon and the minimal numbers of samples in each cluster. So for, try to go through some values for epsilon and some values for the minimal number of samples, and let's see what will happen. Okay, if our epsilon is little for our task and we have um, yeah, and we chose okay, if epsilon isn't enough to capture um, a lot of number of neighbors for each element, in this case, we will select very small groups. Yeah, like that, like here, because um, we we get each element C to the area, and this area um, based on epsilon, and understand have we enough numbers of neighbors in this area? Could we join these neighbors to in one group? Yeah, of course, if we use the the small value for epsilon, in this case, we will see only to the real close area to each vector, and yeah, uh, couldn't join a lot of vectors to one group. Okay, if we keep this epsilon, but we'll make the minimal number of samples bigger. In this case, we just reduced the number of groups what we selected before. Yeah, because each time we see two areas for each elements, and understand this element has enough neighbors for making it making it as a core element for this group or not. And yeah, if we increase this minimal number, when we can make some element is a core element. Yeah, in this case, we just will reduce the number of selected clusters. Okay, if we want to we want to select more bigger areas, we need to increase the area where we will try to search. So yeah, you can see if we choose the bigger epsilon, like 1, we started to select bigger groups. So yeah, and okay, yeah, in this case, if we increase the minimal number of samples, we started to select more isolated group. Okay, yeah, and we can increase the epsilon a little bit more, and in this case, for example, we joined a lot of elements in one cluster, in 0 cluster. So yeah, we have a lot of elements in 0 clusters and a lot of elements without cluster. Yeah, the label -1, it means that this element doesn't have some cluster. So yeah, and if we joined a lot of elements in one cluster, and we want to to split this group of elements to uh, to more clusters, we can increase the minimal number of samples. So yeah, try to do that, and yeah, we can see here that min samples isn't enough for beginning splitting this big cluster to many different clusters. Try to increase a little bit more, and yeah, we can see that, for example, when min samples is 11, it started to work. And for example, we selected some these clusters. So the last thing what I want to say about this approach, that in comments we use Euclidean distance, and here we tried to use the Euclidean distance too, but if we are working this DBSCAN, we can try to use other metrics like cosine similarity. And yeah, we can try use cosine similarity, and in the most case, I think the cosine similarity is better for working with texts. And yeah, what what we will can to try more. For example, now we reduced the number of our features using using PCA, but we also could try to use Word2Vex for reducing our features. How it could work? You can you can try you can download the the list of pre-trained Word2Vex. Often it is a vocabulary where for each token there is the vector, these 300 features. So yeah, and you can transform your texts, your text using TF-IDF, get the vector of TF-IDF, and after that you can multiply these vectors, this vector, these matrices of Word2Vex. So yeah, for each text you will have the vectors, the vector of TF-IDF scores One, these dimensions, one cross the number of your vocabulary. Also, you can get for each token from your vocabulary the vector from the pre-trained word2vec. And in this case, you can create the matrix, these dimensions, the number of your vocabulary, uh, the length of your vocabulary cross 300, and you can multiply this vector and this matrix and get the vector. These dimensions 1 cross 300. And yeah, this approach, it is about reducing the representation of your vector tool. And you can try to use this approach for reducing the number of features and apply, for example, DeepScan. And in this case, the cosine similarity will work good. Yeah. So, yeah, thank you for your attention. It was the last seminar in this year, and yeah, have a great celebrations. So, thank you. Bye.